Now we want to start on probability theory. And I think that you're going to find probability theory is nice in the sense that there's not a lot of new mathematics. And it also involves a lot of applications of things that we've used in the past. Okay, so there'll be a lot of calculus, for example, and we're going to, especially apply a lot of integration theory. Before we get started, it's kind of nice to understand the interplay of probability and statistics. Okay, people sometimes they say them in one, phrase as if they're just one whole thing, probability and statistics. But actually, probability is the theory underlying statistics. Okay, statistics is how we make decisions from data, and probability is really the mathematics that justifies those decisions that we make. So probability theory in a sense is more fundamental. It's much more mathematical too, I may add. One of the things about probability theory that's very useful is to understand the origins of probability theory. So probability really came from gambling. I mean, there's just no other way to look at it. Historically, it derived from people trying to make bets and figure out what are the chances of certain sorts of outcomes in games of chance. And even to this day, probability theory is largely motivated by games of some sort. Usually they're financial games like on the stock market, but nevertheless gambling has a great deal to do with probability. Why is that relevant to you? Well, because it's very useful to think of probability in terms of betting. Okay, we tend to think about things in terms of, what are we betting on? When are we going to win? Okay, these are kind of useful things to have in the back of your mind. Although not all probability theory came from gambling. There's a lot of probability theory that also came from statistical physics too. Okay, so there are a lot of other applications, but gambling is really the main application of probability theory. Okay, so what are some of the fundamental notions? Well, the first one is the idea of an experiment. Okay, and whenever you're starting to look at something fresh, you're looking at a problem at the beginning, it's kind of useful to think in these terms. And so the experiment is basically any process that can occur that yields an observable outcome. Now, there are a lot of different examples that you're probably very familiar with. You can flip one coin, right? That's a process, flipping the coin, and there are observable outcomes, heads or tails, right? You can roll one die, same sort of thing, right? Now, these first two examples are ideas of experiments in the sense that we normally think of an experiment, something you can do in a lab. And really the main thing is you can control it, right? It's a controlled process. But not all experiments are controlled processes. For example, if you observe an earthquake and record the magnitude, that is an experiment, but you certainly can't replicate it. Okay? So experiment's a very, very broad term. Okay, associated with an experiment is the notion of a sample space. And a sample space is just all of the possible outcomes that could occur from a single experiment. Okay? So if we look, for example, at a coin flip, we flip one coin. What are all the possible outcomes from a single coin flip? Well, we know that's heads and tails, right? Now, what's really important to us, however, is an event. Okay? An event is any subset of the sample space. The reason why it's important is because events are the only things we can compute probabilities on. Okay, so when you're trying to figure out what you can compute a probability on, you have to ask yourself, what are the events? Okay? So to understand that, we need a little better characterization of the sample spaces, okay? And so we can talk about discrete sample spaces and continuous sample spaces, and they're important because they have different types of sample spaces and the events are going to be very different. Okay, so a discrete sample space is a sample space where the number of possible outcomes in a single experiment are countable. And this word countable is a mathematical term. It's a technical term. And what it means is that the elements, and I usually use ELTS to abbreviate elements. It means that the elements in the sample space can be put in a one-to-one correspondence with some subset of the natural numbers. It's kind of worthwhile looking at that definition in a little more detail. So notice that sometimes you can have a set that is finite, and any finite set is countable. So think about, for example, if you roll one die, what is S? Well, the outcomes are 1, 2, 3, 4, 5, 6. Can I put that in a one-to-one correspondence with a subset of the natural numbers? Sure. Let the subset of the natural numbers be 1, 2, 3, 4, 5, 6, right? And there's a one-to-one correspondence, the identity map, right? But sometimes S can be countable and infinite. So for example, suppose you look at the number of accidents that could occur in a country, or the number of errors that a person could make, okay, doing some sort of process. Well, in reality, there's probably some upper limit. The fact is that, it's really hard to characterize. So, what are the number of accidents that could occur? There's really no upper bound in a sense, right? And so this is a situation where S is countable and infinite. And there are very realistic examples of things that are countable and infinite. For example, if I look at the number of times I have to flip a coin until I get the first heads, that could be infinite, right? I could keep flipping a coin and get tails, 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 tails. It's possible, okay? So countable can mean countable and finite, countable and infinite. Sometimes people make the distinction by saying something is countably infinite. I'm not going to do that. Either one suffices for us. And of course, events, since they're subsets of a countable set, they're going to be countable. All right. Now, let's compare that to continuous sample spaces. So if we contrast that, we see that in a continuous sample space, the number of elements in the sample space are uncountably infinite. In other words, we cannot put them in a one-to-one correspondence with a subset of natural numbers. That's a very, very broad condition, and so we're going to limit this a little bit. So for our purposes, although there are other situations, for our purposes and for most purposes in probability theory, continuous sample spaces are going to be intervals. Okay? And so events are going to be subintervals of that sample space. Okay, that's how we're going to think about continuous sample spaces. Okay, so let's look at some sample problems. Suppose, for example, we flip two coins at the same time and record the number of heads. That's our experiment, okay? Notice that part of the experiment is what I'm recording and how the process is being done, okay? What is my sample space? Well, basically it's a number of heads I can have in two coin flips, right? So it could be 0, 1, or 2. Okay? Now suppose I do the same experiment, but this time I record the sequence of outcomes. I flip one coin twice, and I record the sequence of outcomes. So I want to know what was the first flip's outcome and what was the outcome in the second flip. This is a different experiment, right? Now what is a sample space? Well, it's all the possible strings of H and T, right? Heads and tails that have length 2, okay? Let's think about the event. Let's think about the subset of this sample space where we have at most 1 heads. Now we said an event is a subset of the sample space, so it's also a set, right? So what elements are in the set where we have at most 1 heads? Well, we have to understand what at most 1 means, right? At most 1 means we can have not more than 1, which means we can have 0 or we can have 1 heads, right? So what are the outcomes in the sample space that satisfy that? Well, they're just the following, right? I have at most 1 heads. These are all the outcomes that either have 1 heads or 0 heads, right? Let's ask ourselves, what is the event that where I have at least one heads. Okay, so if I want to make up a new set from these elements, and I want that set to have outcomes that have at least one heads, what do I have to have? Well, if I have at least one, I can have one or more, right? And so this will be the event. Okay? Okay, we're going to go on and we're going to look at set theory a lot more in the second video.